Yes, it's working. Oh my God. This is great because like you gave a great intro to my talk. That's what we're talking about. We're talking about synergy. Wow, that's a buzzy word. Okay, all right. So this talk is called Stateful Web Applications, right? Just a brief intro to who I am. This is, actually it starts with a picture of me that you might find on the internet. I have this logo everywhere. My name is actually, though, Hannah Howard. And I am a programmer. I'm not particularly somebody of any note, but I do know how to write some web apps. I did not creator of Erlang, not creator of the actor model. But I know something about web applications, I'll tell you that. That's my email, and that little handle at TechGirlWonder is me on the internets for the most part, including the Twitterverse. Okay, oh, and sorry, one more thing, which is, wait, oh, I lost a slide. Oh, well. There was another slide that said that was like a personal anecdote about me that had a really cute picture of my dog. So just imagine there's a cute dog, and that I actually like dogs, and now you feel comfortable with me because I'm a human being. Okay, so, okay. All right, so this is a talk about Elixir and Phoenix, and it is somewhat geared towards folks who are switching languages away from one of the other traditional web programming languages, such as Ruby or Python or maybe even the PHP, right? So that is who it's sort of geared towards, but big caveat, the goal is to give all of you who are in that position a very different perspective on why you want to switch to this new language, right? Wait, there's like many slides missing in here. Oh yeah, well, in any case, I'm going to continue onward. I apologize. I think I've got an old, sorry. Can I just give me 1 sec, because I'm like missing serious slides here, and I didn't do anything, and this is making me feel awkward. Okay. What happened to the other slides? Weird. Okay, you know what? I think this room, oh, see, there's the dog. See, look at the dog. You know what? What? Yeah, no more of this fancy remote that that was a fool's errand to try to get that. Okay, yeah. So this talk's going to go in a lot of different directions, but generally a few things that we are going to cover are, first of all, why people in those other web worlds are now switching to Elixir and Phoenix, why they're doing it as it is. And then we're going to talk about, in much more broad terms, about how you build web applications, how we've traditionally built them, versus the kind of Erlang model for building any kind of an application. And finally, we're going to look at how you can use the fundamentals of Erlang and OTP to enhance web applications you might write in Elixir or Phoenix. Okay, so continuing on. When I wrote this talk, I didn't check the speaker list first, so I didn't see that like Joe Armstrong was on there and like all these folks who's like, I'm going to be talking about the history of Erlang and the actor model, and I didn't imagine that those folks would be in geographic proximity when I was doing that. So if you're coming from the Erlang world, you just keep your mind open in this talk. I think you might learn something about where I'm coming from and other folks are coming from in the web world, right? So just keep an open mind. Okay, so let's get into the meat of the talk, which is, and start with essentially the perspective I hear from a lot of folks who are switching to Elixir and Phoenix, right? And I'm going to use the specific example of Ruby because that's kind of the biggest vector. So this is what I hear. I hear somebody say, I want to use Elixir and Phoenix because it's just like Ruby on Rails, but faster, right? And that's kind of like, it's like, oh, I just want the things I always had, but just a little better, right? That's cool, right? That's all right. I mean, the reality is, especially if you're coming from like Ruby, yeah, Elixir or Erlang is generally faster because it's a compiled language, and it's going to be faster. But if you were to ask, like, if your simple goal was, I just want speed, right? Like, and especially if you're thinking in terms of like being able to just execute a linear process really quickly, like you could do a lot better than Elixir and Erlang. You could be in C if you were really serious about like being super duper fast in terms of your processing power, right? So let's rewind a bit and ask, like, why don't we write our web servers in C? Because, dude, then they'd be like super fast, right? That'd be awesome, you know? Well, so here's the thing, right? Faster has what is faster in the context of a web application or a web server, right? It actually has some very unique properties, right? So faster in the context of a in the web server primarily means being able to serve many people who are visiting your website at once, right? So when you write a web server, your goal, if you're, particularly if you're in a startup hoping to grow, is to eventually be serving, millions of people per day and be getting all of these, web requests, and your server has to coordinate all those and essentially be able to handle them without getting bogged down. So it has to be able to, in some ways, manage doing many things at once, and we call that concurrency, right? So that's a unique aspect to how web applications work. But there's another aspect. So web app. Sorry, I apologize. And that is, and to answer that, let's rewind a little bit further and ask ourselves a slightly more broad question, which is, what is a web application? So a web application is an interesting thing, right? Your goal in a web application is you're actually like running an application that serves millions of people at once. And the way you do it is you use lots of computers to do it, right? You don't just run a web application on one computer. Even if you only have one web server, right? Your web application has a server, and then it has everyone else who's viewing your website is using their computer, and they're using their web browser to view your website. So you're delegating some of the work, even in in an extreme case, to the user's computer. So you essentially, every web application is an application that runs across lots of computers, and they're all connected through the internet over a network, right? So there's this computer science-y term for that, and that's a distributed system. A distributed system is a program that runs across many computers connected by a network, right? So this is interesting because there's a really important thing about distributed systems. They're hard, or probably they're not hard to everyone at this conference, but they're hard to like most people. Yeah, for most folks, they're pretty hard. They're hard to think about. They're hard to reason about, right? And they have some really unique, challenging properties, right? So the first one is that they have to be able to scale. Meaning that if your program is using 10 computers to serve 100 people, eventually, if you're lucky, you're going to be using 1,000 computers to serve, hopefully 1 billion people, right? Well, here's the problem with that, right? You might have this idea that, like, okay, figure out how many people do I need to serve, and based on some constant number, I can just multiply that and get the number of servers I need to run, right? And it will just grow linearly. Well, it doesn't really work that way, right? Actually, what happens is essentially, as your users grow, your number of machines can often grow exponentially or even geometrically, or it just doesn't work at all. You get to a point where no matter how many servers you add, because their coordination and essentially they end up all waiting for each other in some fashion, right? You actually are not able to serve more people no matter how many machines you have. So that's the problem of scalability. So there's one more big problem, right? And that is, how do you manage state? So to answer that question, I want to rewind one more time, and I want to ask a pretty almost philosophical question, which is, what is state? Okay? So state is like, I use it probably every day in my job as a programmer. Very rarely do I stop and think about the actual definition, even though I kind of have it in the back of my head. So I want to give you a quote that will hopefully illustrate the nature of state. Okay? And this quote is from a book. Okay? So the quote reads, "All that you touch, you change. All that you change, changes you. The only lasting truth is change, and God is change." So that's from a book by someone named Octavia Butler in a book called The Parable of the Sower, which this may be the moment in the talk where you're like, what talk did I just come to? This is getting a little existential. I'm going to bail. But I want to like try to illustrate why I use that quote, right? So I'm going to define a stateful application as an application that essentially the way you interact with that application changes as your interactions influence the internal condition of the application. So essentially, as you change the application changes in the way, and that results in different ways of interacting with it, right? And so we call that internal changing condition of the application. That is what we call state. State is the internal condition of an application, right? So there's a bummer thing about state as well, which is that managing it kind of sucks. Managing state is really difficult, particularly if you let it get spread out over just sort of like over the course, over all around your code base. It becomes really hard to track and really hard to like figure out like who's modifying it at any given time. So almost all the solutions that have to do with managing state have to do with kind of like isolating the state the sort of storage and changing of state into different parts of your application. It's becoming more and more of a thing in the web world. I even originally had a slide about how state is like very passé these days in the web world, even though obviously it's necessary. So it's kind of hard, and then it gets extra hard when you're talking about a distributed system, right? Managing state in a distributed system is really difficult, and I'll give you a good example of why. You could argue that managing the state in a distributed system is why marriages fail. The state of the marriage is spread out across two people, and they're constantly trying to sync up their state, right? But unless they've got really good communication, then they're going to get super far out of sync, and then things are going to go poorly. Okay, so that's state. Let's talk about what the rest of this talk is about, right? So we have defined distributed systems as we define distributed systems as these difficult things to build. And so what I'm going to talk about for the rest of this talk is two great models of distributed systems that are concurrent, that scale well, and that manage state well, okay? So the first distributed system I'm going to talk about, it says what we've always done, and that would mean what we've always done if you're a web programmer. Some of you may have another thing you've always done, and you stay tuned. You'll get your turn. So anyway, so there's what we've always done, right? And this is the thing, and a lot of web programmers don't even know that we have this system, right? That they're kind of working within it. So it's like a system that you may not be aware of, but when I illustrate kind of the constraints of it, you may understand a little bit more clearly about how it works, right? And this is something you've used if you've done any kind of traditional web framework type programming, Ruby on Rails, Python and Django, PHP, and whatever people are using these days in PHP. So the first constraint of this system is HTTP, right? So HTTP, they say it is a stateless protocol. And what that means specifically is that essentially when your server gets an HTTP request from some browser somewhere, it actually doesn't know anything, it doesn't have any information about what that browser is actually doing other than what is contained in the HTTP request. So it knows nothing about the browser, and meanwhile, the browser really knows nothing about what the server is doing, and other than what gets sent back when once the server processes the request, it sends back a response, right? So there's essentially no knowledge about the other party, and so we say that protocol is stateless. There's another part that we make stateless in a traditional web application, and that's the server code itself. Right? Sometimes we actually call like this model stateless web applications. What we really mean is the application code of your server is essentially stateless in the sense that when you get a request in from a client, you do stuff, you process that request, you might set some variables, you might put some stuff in memory, and then you produce a response. And then once you're done, everything that you put in memory, all of the state you've created, gets thrown out for the next web request. So each web request, it's like your code has no persistent state of any of its own, right? Well, so obviously you still have to have state in order to like write, cool web applications. So we have a solution for how we manage the state. Anybody like have a guess as to what that solution is? Oh, wait, I heard it in the back. Say it louder. Database. The database, yes, yeah. So like, basically, like the big solution is we're going to punt on state. We're going to hand it off to these relational databases, which, to be fair, are really good at managing state, right? On the whole, they've been around for a long time, and they've gotten really good at managing state. There's one other thing we use to manage state, and that's the little, this little add-on to HTTP, which is you call it a cookie. It's essentially a little bit that you send back and forth in the actual request response cycle, and that, and the cookie usually contains some unique information about the person viewing the web page, namely who is viewing the web page, because that's often very important to be able to provide a unique experience based on the user who's logged in, right? So those are kind of the state solutions, and then the concurrency solution essentially is to delegate to the operating system, right? The idea is if I need to process two web requests at once, I'm going to, when I'm writing a Ruby on Rails application, I'm going to spin up two Ruby processes, and, and then they'll just process, when the requests come in, they'll process, and we'll hand it off to the operating system to figure out who's going to run at any given time. Because operating systems are actually really, really good at switching between processes, right? It's something they've gotten good at over several decades. So anyway, yeah, so that's great, and it works because our server code is stateless. So you can run them both at the same time and just rely on the operating system to handle it. One other thing that we tend to do in this model is when we need to do something that lasts beyond the request response cycle, we'll use some sort of mechanism to create some kind of a background job. In Ruby, you might have used something called sidekick or rescue. So that's another sort of trick that we use. And then the great benefit of all this is that, with all these things in place, you can scale your server to a large extent because your server code is completely stateless. You're getting stateless requests. And so if you need to serve more clients, you spin up more processes on your machine. And then when you run out of processing power on that machine, you just spin up another machine and add more processes, right? And that's great. But there's a bottleneck in all this. Anybody know what that bottleneck might be? The database again, right? Yeah, so there's this problem, right? Because you're throwing everybody has to go through the database. So eventually you're going to max out the database, and then there's a bajillion so-so solutions to try to deal with that. Database sharding, all kinds of people have a whole job title based on this. They're database, DBAs, so because this is such an important part of the application. There's one other kind of like bottleneck in this, which is it's not particularly good for real-time stuff. You're tied into this request response cycle, and anytime you need any state, your server has to make like a round trip out to the database, which is technically actually a network call, even though it's often on the same machine. So it is not super fast. So that's another constraint, right? I would argue that all of this system, which is pretty well architected, has an underlying constraint, right, that is almost hidden. And that is, it's all set up to run for a traditional programming language, right? So a traditional programming language, you essentially, your program boots up, reads the first, instruction of code, and it goes and executes them sequentially, and it might jump around because it might have a loop in it, or it might split off on one path, but it's essentially one interpreter moving linearly to the end of the program. You have a couple of sort of workarounds that operating systems provide and most languages support, such as threads, right? If you want to try to run two things at once within the same process, but they're generally extremely difficult to work with because each thread, they share memory, which means that all kinds of problems come up. I'll just sort of keep it at that. Right. Okay, so that is the model for web programming, right? So then there's this other model, which I realize in retrospect could also be titled What We've Always Done, and that is the Erlang VM and OTP, right? So this is a totally separate model, and again, there may be some stuff that I'm coming up on that for some of you Erlang guys and gals, this is old hat, right? But just stay with me, right? So let's talk about the Erlang VM and OTP, and this is particularly targeted towards those of you guys who are really basically web programmers, right? Okay, so to talk about this, we have to rewind a bit and go back to the 1980s, so this is before the web even existed, right? There was a research paper probably at some point, but for the most part, there is no World Wide Web, right? So the telephone company Ericsson, again, this is like all based on the assumption that the people involved in this are not going to be sitting in the room, and that might be true. So this telephone company called Ericsson, and they had this problem, which is we've got lots of telephone switches. We've got a huge telephone network, and there's all these little routers that route the telephone calls all around, and we need them to work, and we need them to run really well and not fail, and also be able to route all the telephone calls. So it's a distributed system, right? It's a program that runs over lots of boxes. And so their solution was, we're going to write a new programming language, right? And that program that is really well suited to this problem. And the very underlying basis of that programming language is this thing called the actor pattern, right? So actor pattern is a new model for building computer programs, right? So, it's an alternate model to object-oriented programming or procedural programming. And the way the actor pattern works is essentially an application is built out of several actors, right? And you can think of these actors as like little units of code, similar to the way you might use objects within an object-oriented programming language. And but the thing that's unique is actors are completely separate from each other. So your program is made up of all these independent actors that know nothing about the state of the other actors. But what they can do is they can send messages back and forth, right, between the different actors, right? So I may not know what you're doing, but I can send you a message asking you to do something, right? Now, the thing that's really unique about this is that the message passing it's not synchronous. When you send a message, you're essentially giving up control, and the other, actor may process it immediately, they may not. We actually pass messages, if you've done object-oriented programming, we pass messages quite a bit, but you may not even be aware that you're doing it because the way you pass a message in most object-oriented programming language is you call a method, meaning you expect that code to run immediately, right? So it's not like that in the actor pattern. You send messages, who knows when they'll get processed, right? You essentially give up that control, right? And the one guarantee that you get is that from the standpoint of the person processing incoming messages, they're going to receive those messages in the same order that they're going to receive the one that was sent first, and the one that was sent last, right? It's actually somewhat similar if you just think of it as an email system, right? There's a lot of similarities, right? Your inbox, if I send you an email, that's the point at which I'm giving up control and saying, I hope that person likes me enough to respond to my email, right? So it's a similar type of thing, right? And arguably, this theme came up once before, which is that like the actor pattern, if you look at it and you look at the early sort of like object-oriented programming theory, like in some ways it's closer to what the original folks who defined object-oriented programming were talking about. And there's lots of snarky remarks that go along with this, but I don't have the quote on this in this presentation. Look at some of your other speakers for that. Okay, yeah, so that's kind of the model, but how does it all work, right? And the way it all works is with the Erlang virtual machine, which is a platform on which all of your programs run, and it has this thing called a scheduler. And the scheduler is the thing that is responsible for figuring out how all these actors are going to run and in what order they're going to run, right? And switching between them, right? Because essentially your program is no longer like a program. It's a whole bunch of programs that are just wanting to do their own thing, right? So you have to have something to kind of like manage between them. And essentially the way the scheduler in Erlang works is it is very similar to the way your operating system works switching between programs. So in Erlang, the word that we use for actor is just a process, right? Because each actor is like its own computer program, right, in many ways. And then the thing that coordinates all those is the scheduler. But before we get into that, I want to do a quick digression into the difference between preemptive and cooperative scheduling. I find this particularly interesting just because I've been around long enough since when this was an issue in operating systems. But there's two different ways you can manage multiple programs at once. And one is called preemptive scheduling, the other is called cooperative scheduling. The best metaphor that I have for this is if you've ever like walked into a classroom with like small kids and a teacher who really has no control of the classroom, right? And the kids are just doing what they want. That's like very similar to cooperative scheduling, right? The model of cooperative scheduling is basically like a process is doing its thing, and when it's like, I think I'm done now, it's like, hey, operating system, you can switch to someone else, right? So the operating system is dependent on the program giving up control. Preemptive scheduling is if you've ever seen a classroom where the teacher is in control, and they're like, no, you're not talking now, that one's talking right now, right? And they can even interrupt you like while you're talking, right? Because they've established that kind of like very like intense control. So in a preemptive scheduling model, the operating system can actually just interrupt the running program at any point and be like, stop, I'm going to do something else, right? So that evolution is something that happened over the course of 20 years in the world of operating systems, right? So why replicate it within the virtual machine of Erlang? Well, you can actually get some great advantages by doing this and not just delegating the operating system. The problem with operating system processes is that they take a while to make, and then they take up a lot of memory once they exist. If you have ever used Chrome, and Chrome is famous for running each of its tabs as a separate process, and you keep adding tabs to the point where you have 50 tabs open at once, and not to say that I do this a lot, but I do this a lot, and then, and basically what happens at that point is that your computer grinds to a halt, right? Because you've used up all the memory on your computer because each process takes a lot. Now, Chrome also is just terrible in terms of managing memory, but that's a different issue. Versus in Erlang, in the Erlang VM, you can create a process almost instantaneously, and it takes up very, very little memory. So it's not uncommon, usually as a tech demo, to spin up like 100,000 processes in Erlang and show that you can do it in a second, and the memory of your computer is not like completely consumed, right? So that is why to do that. Now, interestingly, this is not the first attempt, you could argue, at a kind of scheduling in a programming language. So I have a little pop quiz, which is what programming language out there that probably everyone who's done web programming has used implements what I would argue is a form of cooperative scheduling. Anyone? Node? Well, yeah, the language. JS, yeah, JavaScript, right? So JavaScript, they call it an asynchronous event loop because it sounds really cool, but what they really mean is that when that your program does its thing, and then when it like gets to a stopping point, it hands back over control to either the browser or to the Node platform to essentially do whatever has to happen next in this sort of asynchronous event loop. And if you're into like you know, whose framework is better fights, inevitably someone in, not that that's a valuable pursuit, but just to say, like, traditionally the way that like the Elixir person busts out like this is how we win this is if you do you set up a web endpoint that essentially in the middle of that web, the request response cycle, you put a 5-second sleep. And then you make, because sleep is a blocking call, and then you make 100 requests to that endpoint, and you'll find that in JavaScript, in a Node platform, that'll take about 500 seconds, because once your code is processing the request, nothing else can happen. Versus if you look at if you do the same thing in an Elixir or Erlang platform, as soon as you sleep, the scheduler is just going to be like, I think I'm going to switch to someone else because other people are waiting. So. So that's really a great advantage of the sort of preemptive model. There's one other advantage. Is anyone in here old enough to have used Windows 3.1 or like a Mac OS 7, Mac OS 8? Yes, lots of people. I did this question in LA at like a young little hip people web meetup. So there were a lot less hands. Anyway, so so I use these, and these days you use your Microsoft Word, and you're like. You're going along, and then like it shuts down. You get this unexpected error. Program quit. You might have lost your work. You're like super pissed off, right? But just to say, you've actually got it good because does anyone remember what might happen if that happened like back in the days of Windows 3.1 or like Mac OS? What's that mean? Yeah, your whole computer goes down. You don't close the little like quit window, you reach down, you press the power button to restart your whole computer because that's where you're at. Basically, if you're a cooperative scheduling and your program truly locks up, then you can essentially prevent the operating system from ever taking control again. So those are the sort of like really fundamental parts of the sort of Erlang model. And I want to talk just briefly about how some additional stuff that Erlang does to manage state. right? So Erlang is it's a function, it's a functional language. I imagine everyone here is like pretty up to date on this stuff, but and so essentially nothing is, your state can't get mutated. You can't change little parts of it. You have to essentially copy it and create new versions. But because processes are essentially, they can run for as long as they want, they can have their own internal state. And even though you can't mutate state, you can essentially mutate it by having loops of functions that do some processing and then produce a new value for state and then just feed it back in, right? So so you can actually, you kind of have all the building blocks right there. But you could use maybe a little bit more help, right? And so Erlang gives you the OTP, which I describe as a standard library on steroids, right? It's essentially like if you've used any programming language, it has like some libraries that are built in, usually to deal with like math functions or string functions. But Erlang does lots of that, maybe a little bit less on the strings, but like it gives you some really cool tools to work with concurrent programs and in distributed systems and to manage state within that. So what these are is really all they are is a few patterns that developed over the course of like 20 years of folks programming in Erlang. Some of the folks who did that programming might be in the room. But in any case, over the course of 20 years in building these programs out of these really small building blocks, they noticed some really key patterns for how you can manage state in a process and how you can manage state in a distributed system, right? And so essentially they codified those patterns into these little abstractions that you can work within, right? If it were to be marketed in the future, the marketing slogan would be something along the line of, we'll supply the abstractions, you just write your own custom app implementation within it, right? So I'm going to talk very briefly about what those abstractions are. This is not like a let's dive into OTP talk, so I just want to give you a sense of them if you've never touched them before. And essentially these abstractions, we call them behaviors, and they're essentially ways of writing processes that handle state. And I want to talk mostly about one particular one, which is kind of the building block one that a lot of people use well, I don't want to say more than all the others because I haven't programmed enough. Yeah. So there's this thing called the gen server, and a gen server is a process it's a model for a process that maintains state over time, right? So it's a process that's running, it has internal state, and there's basically two things you can do to it. You can send it a message saying, essentially, send it a message and say, I want to reply, you do what you want, and then I want to reply back on the results. Or you can send it a message and essentially give up on knowing what the results are. You can send it a message and say, you do whatever you want to do with this, and I don't really care what the results are. You can think of that as almost like sending a command to the gen server, right? So then the gen server itself, essentially to implement it, you just have to implement two different functions, right? And those functions, the first one's called handle call. And as the name might suggest, this is essentially to handle when someone sends you a message expecting a reply. So so we call that a call, and the call essentially gets three things in. It gets the message that was sent to you. It gets an ID for the person who sent it, and it gets the sort of current state of the. Oh my goodness, I'm sorry. I have to pause because I realize that I do not have this plugged in, and it's about to run out of power, and that would be awkward. Okay, sorry for the delay. I thought this was plugged in. Yes, any power cable that works with a MagSafe 2? Yes, so sorry. Apologies. Yes. I took a 40-minute trip to Best Buy to get that adapter that didn't work, but I did not plug my computer in, so I don't know what that counts for. Where are the? Yes, thank you. Sorry. What? The good thing you work with Erlang is fault tolerant. Yes, yeah. I'm like a process. I can go down. I'm right back up. In fact, let's get going. Yeah. We're back up, right? Somewhere there's a supervisor watching over us. It's like a philosophical supervisor.
Quick comment on scheduling. We have 5 minutes scheduled, but because we started late, we're going to go a little bit late. That said, it is a coffee break, and if you're a little late to the coffee
So I got like 10 minutes, right? 10 minutes, like, before I'm a bad person who's going over the limit. Okay. All right. Cool. Yeah. Then it starts to be annoying. Okay. So anyway, so you got the message, who sent it, and the current state of this gen server as the third parameter to your handle call. And basically, inside the function, you do whatever processing you want to do, and then you send back. You essentially send out back this object we call a tuple with 3 different properties. One is the type of the reply that you're sending. It's usually essentially the status, right? Which is usually either something along the line of reply or error. And then you can send back any kind of additional data to the person who sent the message to give them more information about your gen server. You could even send the entire state of the gen server back if you wanted to. And then lastly, you send back as a third parameter a new state for the gen server. And then when it loops around again, essentially that third parameter, the next time you get a handle call, this current state will be whatever you returned the last time you ran the handle call function, or the other one, which is handle cast. Right? Handle cast is essentially the same pattern but simpler, because you do not have to deal with a reply. So you just get a message in the current state. You send back a type of reply, which is really usually just no reply unless there's an error, and a new state for the gen server. So so the cool thing is, with all this, state can kind of persist in a gen server as long as it's running. There's no limitation. I mean, this is totally separate from a web request response cycle, so it can live around for as long as you like. But there's a question that probably comes up, which is like, what if it crashes? What if something goes wrong that causes the process to crash? Well, essentially, Erlang gives you one additional behavior that's a special one, and that is this behavior called a supervisor. And the supervisor's basic job is to manage the other behaviors and restart them if necessary, right? And so supervisor, you essentially, when you create it, you just give it a list of the little workers it's going to manage, and then you give it a strategy for how it's going to restart those workers if they go down or if they just end, right? Supervisors themselves can actually have children, which are supervisors. So your application ends up consisting of essentially a tree made up of a supervisor at the top, potentially more supervisors as children, and eventually down to a bunch of leaf nodes, which are the actual workers, right? Just a caveat about this does not necessarily solve the problem of recovering state, and it's probably important to think about if you want to start throwing lots of state in your gen servers and you expect them to last indefinitely. One other nice thing about OTP is that it does give you these tools that are specifically great for this type of thing. It gives you actually 2 databases, right? There's a really simple one, an in-memory database called Erlang Term Storage. And there's a more kind of like traditional but really well built for a distributed system across many computers called Amnesia. And so you can actually use those to, in a worst case scenario, save the state as the process goes down and provide it when it spins back up and essentially keep it around indefinitely. There's lots of other tools. I think I'm just going to go through this because I actually do want to end on time. But like static code analysis, like there's all kinds of crazy tools in the OTP. Forget it. Okay, moving on. So yeah, there's like I said, it's a standard library on steroids. But anyway, we now finally come back to the original question, right? Which is what we started this talk with. Why would you use Elixir and Phoenix? What are Elixir and Phoenix in the context of this sort of Erlang ecosystem, right? Well, Elixir, hopefully this slide won't be too controversial. You could describe Elixir as essentially like the marketing slogan would be to the young, not young, but essentially to those who've gotten accustomed to like web conveniences like a package manager and a specific type of syntax that people are usually, it's kind of somewhat shared between Ruby and Python and all the other web languages. Well, so you could say that, essentially Elixir is Erlang updated for the web generation, right? So then what's Phoenix, right? Well, so Phoenix is a web framework that is built on top of Elixir and the Erlang VM. So it's a web framework built on top of this really crazy, amazing distributed system model over the Erlang VM that we've been talking about, right? Now, if Phoenix had a marketing model, it would be like basically the same new language, same patterns you love. It's like you come to a new language and you already have like the Matt Damon of the language. It's really reliable. You already know it really well. And you can just keep programming the way you've always programmed if you're a web programmer, right? You can use the tools like HTTP and relational databases, and all your stateless, all your request handling can be stateless, right? It's wonderful, right? But you could easily miss something. And this is the heart of the talk, and this is particularly directed towards to the web programmers, right? And that's not all you have. You have this immense tool set with amazing powers, right? You've been ignoring it for so long, but you never know what could happen. Well, yeah, it's just got a lot of power. In any case, so it's really amazing because what is better than one great distributed system model is like two great distributed system models, right? So that's great. Okay, well, in the abstract, it's great, but in reality, we're actually entering a really interesting uncharted territory, right? And this is getting back to my intro, which is synergy, right? This is I don't know if there's ever really been a time when these two giant sort of distributed system models have come together to sort of see what happens, right? So the question then becomes how do you mix them? How do you mix a standard web distributed system with the kind of Erlang model? So couple of answers. And this is a little bit on the speculative side, and these are my own answers to some extent. So first of all, if you're using Phoenix, you're doing it already, even though you may not know it, right? Phoenix under the hood is built upon a couple of OTP processes and essentially the Erlang model. Particularly in this case, you're actually using it quite a bit if you're using any of the fancy new features in Phoenix. There's this new thing called channels for doing WebSocket-based communication. There's another thing called presence for tracking a state across multiple systems and over time. And all those things are completely built upon OTP primitives, right? There's another answer, which is you could do the things that you might be doing in another language super easily, right? There is no reason to have a background job processor in Erlang because you already have one, the gen server. It's much simpler, it's much easier. If you really need to do a background job, you can just essentially spin up a gen server to handle that, right? Or there's even simpler abstractions within Elixir, right? The larger answer is I'm not 100% sure, but here are some ideas, some thoughts of ways you could do this, right? First of all, if you're doing something real time, maybe let go of the database for it, right? If you're tracking state that changes rapidly over time and isn't really that permanent, there's no need to use a database. So I'm actually going to give an example from this thing that we're doing in LA with the LA Elixir meetup. We've been building a group project together to essentially simulate the werewolf game. It's like a party game, right? And our idea is we're going to build this server that people can log into and join game rooms. And then within the game room, essentially in real time, you'll start a game and all the players will be updated and they'll take turns and all that stuff, right? So interestingly, we are storing one thing in the database, which is the game room's existence themselves, right? We're storing a list of game rooms because game rooms are going to last forever. But the game itself, once you start the game, it's completely within a gen server process, including which players have joined that game room and as it happens, essentially as the game server is happening. And I think it's an interesting model. It seems to work well. So in that case, the game itself is a very real-time thing versus the sort of permanent thing is the existence of these game rooms. So that's an interesting way to divide it up. Another rule is if you're taking something like database-y that has to be distributed across multiple computers and scale, maybe this is your opportunity to step out of the relational database framework, right? Obviously, I've already mentioned that there are database tools included within OTP. There's also this other giant independent database solution called React, which I believe there was a talk on earlier, that's really amazing for storing a highly distributed system across lots of computers, right? You might also want to consider other solutions like Mongo, but you might also not want to because why would anyone use Mongo? Anyways, so Yeah, so that's possible rule number 2. Possible rule number 3, this is just another idea, which is like, you've got this great like in-memory store way of tracking things. Use it as a cache for your database, right? Like if you're gonna read something from a database lots of times, right, and it's one big table that you're just reading in and out of, like you can actually create an in-memory store as a way of essentially being an intermediary, and then you only go out to the database when you haven't read it before. Now there's obviously, cache invalidation is not always an easy thing to deal with, but it's something you could do, right? One other thing that actually is there's actually this, when you get the link and you actually, if you visit this presentation online, that's a link to an article about how you would actually implement this. Another thing that was interesting, someone in LA came up with this really crazy, cool mixing of the database and OTP, right? And what they were doing, and so this rule would be like, essentially use databases for what they're good for, which is like CRUD type operations in a web server, and then use OTP for everything else. So what they did is essentially they were building a build system tracker to track builds as they were builds of some kind of program as they were going, and they would essentially kick off a build and write an entry to the database. But then they would use an gen server and actually some other things to do all of the tracking of that task and then updating it in real time, right? So it was a really interesting solution. That's also a link to that. One other thing you can look into is using OTP to do stuff in the web you've never done before. So one of the amazing things that Erlang offers is the ability to deploy parts of your code without taking down your entire program. So look into it. Figure out how you can do that within your web application. So I'm going to get to 2 final cardinal rules, which are the wind down of this talk, because I know we're about at time. And basically, the cardinal rules are these, right? If you're coming to this world from the web, if you're coming to Elixir and Phoenix from the web programming world, and you don't know that much about OTP, or if you're one of the folks who's like coming here and you know OTP, but this whole web thing seems pretty weird and new, go ahead and spend some time to learn the other model, right? Don't just stay within your lane, explore what's possible. And then the other cardinal rule, which is number 2, is once you have a familiarity with both, like, be creative. Come up with new solutions. This is actually a really wide open world, and we're all going to discover new rules, right? When I started this talk, I intended to answer this question, which was probably indicative of an intense amount of overconfidence. But I'm comfortable not answering it because I'm really only now understanding what is possible and what this problem is, right? And so I think, as it turns out, we're all going to have to figure this out together, right? And so in closing, I'll just say good luck, and you're going to need it.